it's like, I was like going through and like, an ore should have a fairly high amount. So I was like, I got 50, like, saw 56%. I'm like, that's a fairly rich ore. So I was like, that's what I put in my library paper. Didn't put much more question around it because I figured it didn't need to. Now when you get 6%, then I definitely would question it. And that explains why Alex's group is asking me what the, because they must have got a weird number too.
Yeah.
Whoever Alex is, one of
One
those
of
two.
Yeah, I think Soda's not in this class though. Isn't that like
Okay,
or
well,
something?
thanks for
Yeah.
still considering to continue your effort in getting through the course. Who we are and what are you doing? Where did we stop last time?
We were talking about the infinite square well and the discretized solutions to it.
Okay.
Oh yeah, we started talking about the density matrix of the coefficients
Oh, correct. But what is the goal?
to describe a realistic situation and what's going to happen.
What do you mean a realistic situation?
Like a chemical reaction, I would assume.
Development in time.
Yeah.
Okay, so we are not looking for static properties, but looking for development forwards in time. For the simplest possible, well, second simplest possible situation. And the main conclusion of our meeting today, in whatever 40 minutes, we will declare a conclusion that you actually know it. If the system resides in a non-stationary state, in a superposition of eigenstates, then it will evolve in time. Some observables will change with time. And even if you are not touching observables, if you're looking only at some simplest thing that can be interpreted like probability distribution in space, it will be not static, but it will change somewhere, which we can interpret as claustrophobic electron bouncing force and back between the walls. And the walls are, why do we need the walls? What do we describe?
Molecular boundaries?
Yes, like if the electron reaches the end of the molecule, and then there is a vacuum or some dielectric, then it's like a wall, it cannot penetrate. Okay. So you probably are feeling comfortable with just putting the figures and bringing it next time, right? It is where we are now, so there are methods and there are systems, and we went through a free space electron, and now we have a simplest box. And in addition to Schrödinger equation time-dependent, time-independent, there is a, well, this time-dependent Schrödinger equation is very related to so-called density matrix. So where did we stop last time? We agreed. Well, first we considered that we have only first and second states in the box, and we have excited by 50% with laser or whatever, and we are in a superposition of ground and excited, and we are looking for probability distribution of whatever x or z position and time. And we came to intermediate state, intermediate situation, intermediate description, where we agreed that dependence on space and time can be split not only for wave function, but also for probability distribution. So we can have a products of space distribution and time evolution factors. Okay? That is where we stopped last time. And we have agreed that time evolution factors that come from the product of the expansion coefficients from the initial conditions time accumulation of phase can be referred with the keyword with the term density matrix. But it doesn't matter. The time evolution comes from product of the expansion coefficients times phase accumulation, right? It doesn't surprise you, especially based on a lot of time we spent at the beginning about 3 ways to predict future, the time evolution operator, right? Bohr model, accumulation phase. And for our 50% excitation, we do have 1 over square root of 2 expansion coefficients. They're real, so whenever we have the conjugation, we can neglect regarding these initial conditions. And these energies are eigenenergies of the system that we are considering. In the harmonic oscillator, you have an equation that we can recall if we need to, right? Something like n square L h power square h power square 2s. And those eigenfunctions will be sine functions of different ways. So what we are going to do now has nothing to do with science. It will be pure and boring math. We are going to plug in these components into this expression and then plot what we see at different time spots. So on the lab, in your homework, and last time on the screen, we had a computer do it for us. Now we will pretend that we are a dozen of pretty little computers who perform all operations by inside ourselves. Suppose that we are, whatever, 50, 80 years ago when we do not have all this equipment. Any questions now? No? So it is about where we stopped last time. So the summation from the previous slide is over I and j. Since we have non-zero expansion coefficients only for I and j equals 1, 1, and 2, so the summation will cover over 4 terms. 1, 1, 2, 2, 1, 2, 2, 1. Right? 1, 1, 2, 2, 1, 2, and 2, 1. And here we do have the first expansion coefficients, products, which will 1 over square root of 2 will come to 1/2. Then the time factor, and then the spatial distribution. So for the time factor, again, if you look back, it is e to the power minus 8 over h bar, and then e1 minus e1 times t, which will be 0, right? Give me some signs that it's very trivial. You don't want to listen, right? Same energy gives 0. E to the power 0 is here. So for diagonal elements, when we have these same indices here, there is no phase factor accumulation. Now, when these indices coincide, it will be E to second energy minus second energy, again 0. So no phase accumulation. And here we have pi without any factor. So sine square pi x over L. Is it clear where it comes from? Yes? And everything should be multiplied at the front to the normalization factor. I'm just skipping it to have a shorthand notation. So here for the 2,2 element also no explicit time evolution. But if you have the cross terms of diagonal terms, there will be explicit energy of state 1 minus energy of state 2, or energy of state 2 minus energy of state 1, right? So something is accumulating. So the phase is accumulating at a rate equals to energy difference. You can call E22 minus E1 equals delta. And then it is multiplied by, well, by time for sure, and it is divided by h bar so that it will have dimension of frequency. When multiplied by time, it will be dimensionless argument 3 and 1. And here we have a product of wave function phi 1, phi 2, here phi 2, phi 1, right? So sines of different powers. So no science, only math. So we need to process this expression and draw snapshots. We need to draw snapshots of this expression at different points of time. You can try to compete with the board and do it on your notebooks. And I will go slowly but surely. So what is the plan? How are we going to perform it? Do we see any challenges? Just to plug in different values of time and draw. Can you just go to the board and do it? Probably yes. It doesn't need the third or fourth year university education. But why do you do not feel too much enthusiasm? Why do you do not want to go to the board and do it?
It's a lot of work.
Yeah, yes, with action principle. But do you see anything challenging here? Anything that you especially do not want to do? Well, a lot of work means it is several terms. Second, we need to process it at several time steps. But it is just a question of how energetic we are to do crazy silly work. But what are other challenges? Well, imaginary exponential, and there will be trigonometric expressions, right? We do not want to plot products as if possible. We want to simplify it. And if someone puts like a gun to forehead, we will derive all trigonometric expressions, but we try to avoid it as much as possible. Or remember, like, so, oh yeah, I remember them. So, imaginary unit, let's get rid of it. Do you see any symmetry here? Or do you remember our old friend? So, look, here, the powers of this exponent, well, those are two imaginary exponentials, right? But look at their powers. They are the same except the sign is different. So here is 1 minus 2, here is 2 minus 1. And we have plus sign between them. Challenges. Much work. Imaginary and trigonometric. So e to the power plus I alpha plus e minus I alpha. Can you simplify it?
Cosine?
Yes, correct. cosine of what? Alpha, yes. So when I'm going to flip back to previous slide. Attention, careful, I'm not going forward, I'm going backwards. So see, here the space-dependent part is the same. Sine 2, sine 1, sine 2, sine 1. And time-dependent part, so we can put this space-dependent part out of brackets. And inside of brackets, we have exponential alpha, exponential minus at alpha. So this will become a cosine. Okay? So we have, instead of 4 terms, we will have 3. That's a great achievement. So we put this spatial part out of brackets. And this thing will be replaced by cosine of which argument? Delta energy difference, delta E divided by h bar times. Okay? No surprises by now. So we have one challenge less, no imaginary factors. So we have 3 challenges left. Several snapshots, because otherwise you can't go forward in time. Several terms and trigonometry. Okay? So what I suggest we can do is to make a table and see how these 3 things evolve in time. Not the space-dependent part, but only the time-dependent part. After we have simplified it, we can just tabulate it for most representative snapshots of time. Most representative times. Row 1, row 2, and this one will be row 1, 2 plus row 2, 1. Yes. Three snapshots will be sufficient. Otherwise, we will die right here. And looking at them, we will be able to project the rest just by strength of our brain. So, most typical time is time 0. Then we go half period forward, and then quarter period forward and half period forward. This is quarter, and this is half. So this delta E divided by H is frequency, and H bar divided by delta E is a period of oscillations. So we have only one specific frequency. The H bar divided by delta E is a period. So we look at the beginning of evolution, quarter period and half period. And then we can look for the full period, 3 quarters, but we will see repeating pattern. Let's fill the table. Do not hesitate, I will help. Just one cell. We have total 9 cells. 1, 2, 3, 4, 5, 6, 7, 8. I will do 9. Well, let's look careful, going backwards. See, time-dependent part for row 1, 1 is 1/2, and it is not depending on time, so it will be 1/2 for any time period. Yes, thank you so much. See, it's not very complicated.
So then the wave function for number 2, we just want half again.
Mm-hmm.
Right? 'Cause,
Are you math major?
I gotta look back and not, because it was
It's
No, no, no.
1/2 something times 1/2 something. Oh,
Let's
no, plus 1/2 something. That's right.
let's go back.
Right, I can't
Go
remember.
back. So cosine of delta E blah 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 times t,
Mhm.
right?
Right,
So 1/2 times.
because we got one. This is
But
the row that we're
this
looking at,
comes
right?
to
Oh,
this
wait a minute.
goes into. So what is cosine of 0?
1.
Okay, and this 1/2 is already consumed into cosine.
Wait, what now? It is?
Yeah.
Okay. I don't do that much with complex numbers, so I can look
But
at these.
no correction. So it is cosine of 0. Perfect. Yes. Okay. Yes. Thank you so much.
Just like go back. Well, this is 1, so.
So we're looking at this one, right?
Mm-hmm.
Okay, and then the
So no time
Doesn't
depend,
depend
no
on
time
t.
dependence.
okay, so this one here.
Yep.
Okay.
Perfect. Yeah, thank you. It was a safe choice. So now it is the last safe choice. Other two are tricky. Mark, please prepare. Excellent. Thank you.
Oh, it's just not automatic, right? It's, I can see it.
Yes. Thank you so much. Everyone agrees? Right? So cosine of pi over 2.
Oh,
Right?
yeah.
And cosine of pi?
What?
Cosine of pi?
-1.
Yes. Yes. -1. So if we looking only on the elements of density matrix, if you are not looking into explicit dependence on position, we are done. But we want to wrap it up and multiply it by corresponding space distribution functions. You are right. 1, 0, -1, and 1/2 everywhere. Okay. Well, I think it is my part to do something like that. So we will do 1/2 or sine pi x over 2 squared, right? Because we are not looking for wave function, we are looking for wave function. So plus 1/2 sine 2 pi x squared plus sin pi x over L sin 2 pi x over L. And the phase factor was 1, right? For quarter period and half period, I can repeat first two terms, they do not change, right? And here plus 0, and here will be minus 1 of this sine pi x and sine minus pi x. Let's check if I was correct. Yes. So we have squared here, and here we have product. Why do we have factor 2 here?
Because you pull the 1/2 out front.
Yes, we pull 1/2 up front. Why do we pull 1/2 up front?
Because now you can square a binomial.
Yes. Everyone agrees with it? Is it clear what London told you? Give signs if he or someone else need to repeat it. So, see, this is something squared. This is another thing squared. And look, it is two of the things squared, right? So we can simplify it as a plus b squared. What is the sophisticated mathematical verbalization of this? I never speak this language, but I'm happy to learn.
I suppose you could call that completing the square if you wanted to.
Yes, but no. Completing the square, we all speak
That's
this way.
like
Tell sophisticated.
that's the other way. Yeah, I guess, yeah, you could call it a reverse binomial expansion.
Binomial,
Well, like, because the binomial expansion would be going from a plus b squared or to whatever.
reverse binomial
I don't know.
expansion.
I don't know if there's a fancy name for going into the.
It differs from simple language. So completing reverse binomial. Well, on the lower line, when we do have half period, we can do the same thing but with minus, right? A minus b squared. And I do not see too much chances for middle line. So where we are and what are we doing? We have chosen three most representative time steps. We already took into account all time evolution contributions explicitly, and we already have just three functions, which will be space distribution of probability for boxed electron at specific times. So if we would have computers, we would just go forward and plot these three functions and analyze them as scientists. But our rule of game for today is that we do not have computers. We suppose that we do not have computers. And we need to plot these functions. Are they easy to plot? Can you add trigonometric functions in your head and immediately plot? It's not a big wonders. Maybe some of you can. How would you do it if it would be like a homework or exam assignment? Any ideas? Just try to think constructively.
A few points and connect the dots.
No. This is correct, but it is most boring. And there is a human error. If you do not use the gridded paper, human hand can be very shaky at some point in some situations. So and it will take a lot of time. Maybe it will be higher precision, but it is literally replicating what computers are doing. We can do a little smarter. We know how the trigonometric functions behave. But what is not very comfortable is to plot summations. Products is a little easier, right? You can approximately see if you have product of two functions, if one of them is 0, then everything is 0. If one of them is plus and another is minus, then everything is minus. And based on this simple rules, we can qualitatively plot it relatively quick. Especially we know that at edges, at left and right edges, all of these functions are zeros. So we know that we do not need to go below 0 or above L capital. So it will be something that is for sure 0 at edges, and then we need to do some wavy function in between. Another thing, before we go for plotting, this is probability distribution, probability density distribution. Have you ever seen negative probability in your life? Me too. If it is density of electron, have you ever seen negative density of electron? Well, there are concepts like concept of holes in semiconductor physics, but still it is concept in truth, and there is a particle positron in physics, but it is different things. You cannot have negative probability or negative density. So the function will be zeros at the edges, and it will be equal or above 0 everywhere in between. So it already simplifies our task. We can control ourselves. Does it make sense or not? So also, there is one trigonometric relation that I can remember easily in the middle of the night. Maybe you can remember it too. Let's check. So, sine x, sine of 2x. Give me signs if it surprises you a lot. No one is surprised. Can you draw the answer?
Or an identity of that?
Huh?
Or an identity?
Yeah.
No, that was cute.
Nope, that is it. Something like that?
Let's check if it's correct in a democratic fashion. Let's vote for the solution. Who agrees that it is correct? Who wants?
Thanks, guys.
Who votes for some corrections to this equation? 1, 2, 3. 3. Who doesn't have an opinion or wants to hide it? Well, whoever didn't. Okay, so 3 to 4 that it needs correction.
Agreed.
Okay. Let's think as scientists,
So-
not as mathematicians. Let's just interrupt. So, what is sine? Oscillation.
Mhm.
And the argument in front, which if it is sine of x, it is rate. How dense are fringes?
Yeah, great.
Frequency. If you double the frequency, it means that
it's short.
shorter fringes. Yes.
Mhm.
Okay. Good. Who wants to help?
I could throw something out that I'm not confident in, but
Let's- Well, thank you for supporting discussion.
I don't memorize things, I just look them up.
I wanted to distribute like little charts with important equations at the beginning, but then I was hesitant, like, will they upset on me for showing two simple things?
How do I erase things?
Huh?
Just, how do I erase? Or should I just scribble it?
I just, yes.
So,
You lightning and bolt your
Yeah.
half.
Escape.
Lightning and bolt your half.
oh yeah.
Yeah. Who wants to support this result by a vote? 1, 2, 3, 4, 5, 6.
I wasn't thinking that one.
Who wants to oppose this answer? No one. Okay, by majority of votes, we accept that it is a correct equation. So we are going to apply this identity how many times? Everywhere where we have double argument, here, there, and here again. Okay? And here too. And then it will be much easier to plot. So we have about 12 minutes. Just in case, if you forget, well, I don't care about you, I care about myself. If I forget trigonometric equations, how do I derive them? So, write e to the power 2 I x, right, is equal e to the power I x times e I x. True. And now I apply Euler to each side. Cosine 2x plus I sine 2x. On the left side, and on the right, it will be cosine x plus I sine x, basically squared, times cosine x plus I sine x. And then open the brackets, right? Then there will be, for the real part, on the left we will have cosine 2x, and on the right we will have cosine square x, and then last term, I sine square will be minus sine square x. And on the, so it was real part, and for imaginary, sine 2x. So for imaginary part, on left it is I sine 2x, right? I sine 2x. And on the right, it will be I sine x cosine x plus I cosine x sine x, which you can just put factor 2 here, right? And then you can erase imaginary unit. So sine of double argument is 2 sine x cosine x. So now I can forget about Wikipedia and go to the inhabited island and pretend that I'm a little computer. So what do we do next? So everywhere where we had this double argument, we expand it as 2 sine x cosine x, right? And let's pretend that we are parallel computers. Otherwise, it will just be too long. So you'll do all 3 cases instantly. So here was double argument squared. So it was sine, we make it sine x cosine x, and we make it square because it was with a square here. And for the last term, it will be same as in the first. That's no return. Are you following? Should I slow down or it's fine? Okay. What do you see? Do you see any pleasant features in these expressions? Well, nothing is pleasant in math heavy course, but something that can easy our life, make our life a little easier in next minutes. See, here is the sine by x, and here's sine by x. Why don't we put it out of brackets? Right? Put it out of brackets, and the square travels to here too. Then what do we have inside the brackets? We have 1 as an inheritage of the first term, and 2 cosines x with all this variant over L in the second term, right? So sine square 1 plus 2 cosine. Good. Immediately, the last term will be the same with only the negative. And in the middle, can we do similar tricks? Well, we do see the common factor that we can put outside of the brackets, which is sine squared. And in the brackets will be 1 plus 4 cosine squared. Okay? Just summarizing. Now we are going to plot each of the terms and analyze the plotting as scientists. So it should be about 5 minutes, 3 minutes per plot. How do you plot functions? How do we plot functions? If they are products, we can plot one, plot another, and then multiply. Because we do not need literally absolute values. We need qualitatively, just see where other nodal points, other maxima, minima, something like this. So first sine square, and all arguments are pi x over L. So we can forget about pi and L and just do the known trigonometric functions over the half of the range, right? From 0 to pi. So sine square of the stuff. So sine looks like half circle, sine square looks this way, right? No arguing. It is a little lower when it is close to 0, and it is 1 where it was 1. Now, 1. It's trivial. Cosine of pi x over L. So cosine starts at 1, and when we go over half period, then it turns to -1, right? Now, if we do 2 cosines, then it changes from 2 to -2, right? And now we want to add 1. Adding 1 means shifting the whole function on y-axis, or moving the system of coordinates down, right? So we redefine if this will be 0, this will be 1, this will be 2, this will be 3, and this will be -1. So cosine 1 plus 2 cosines will change from 3, then somewhere to the left from the middle point, to the right from the middle point, it will intersect 0, and then it will end at -1, right? What is the square of this function? 3 squared. How much?
9.
Somewhere here it will come to 0. Minus 1 squared.
Goes up to +1.
Yes. So this function will be 1 plus 2 cosine squared. Now we need to multiply this function by this function. How does multiplication of sine square affects our 1 plus 2 cosine? So it doesn't change much in the middle. It is multiplied by something near 1, but at the edges, you multiply two functions, which is the sine square takes value 0 near the edges, right? So the product will have 0 at left and right edges. Then it will have 0 to side of the half, and to the left and to the right it will have positive values, right? You can do it if you need from now on. Okay, for the function that in the middle, how do you do it? So you draw cosine, shift it, and then multiply by sine. Right now we do not have much time, but it will be symmetric function from 0 to L. And if we go to the half period with this minus, we will shift the system of coordinate in different side, and it will be 0 to the other side of the center. So if we add these things together, so movie is a sequence of snapshots. So if you quickly look this, and this, it will look like major peak goes from left to the right. And when we do the rest of progression, then it will go backwards. So all this activity is needed to see how the distribution goes forward in time. If we remember our, just a second, it's not the true end. If we remember what we did at the end of the last meeting, so you see 0, quarter, half, 0, quarter, half. And then we see these oscillations forwards and backwards. So if the system is in a superposition of eigenstates, then observables exhibit dynamics. Conclusion. End of the meeting. See you on Wednesday.